Hi and welcome. This video is the second part of a video series on C# generics. This video is also the second part of the 5th tutorial in a course on advanced C# topics. So in this video we'll create a class to encapsulate the BubbleSort algorithm. This class will be a generic class that can be implemented to sort an array that contains values of any managed C# data type. This will include user-defined types. So in order to enable sorting user-defined types, the relevant user-defined type must implement the iComparable interface. The generic class that will implement the BubbleSort algorithm will contain a constraint as part of its class definition. We'll discuss the significance of using constraints in the context of generics in C#, and we'll demonstrate the use of a constraint through the code example. For more videos on advanced C# concepts and much more, please consider subscribing. And please ring the bell so that you'll be notified of future content released from this channel. Firstly, to highlight the advantage of using generics in C#, I'm going to implement the functionality for this example in a non-generic way. We'll then modify the code to implement generics to create the equivalent functionality. So let's get started. Let's create a .NET Core console application . And let's name this project Generic BubbleSort Application. I'm not going to explain the details of the BubbleSort algorithm in this tutorial. There are many available online tutorials regarding the BubbleSort algorithm. If you'd like me to explain the details of the BubbleSort algorithm, please let me know in the comments section and I'll be happy to make a video on the details of how the BubbleSort algorithm works. Very basically, the BubbleSort algorithm is a simple sorting algorithm that repeatedly steps through a collection of values, compares adjacent elements, and swaps them if they are in the wrong order. Our implementation of the BubbleSort algorithm will work for any array of any C# value type, string data type, as well as any user-defined type that implements the iComparable interface. So let's create a class that encapsulates a method containing the BubbleSort algorithm. Let's first create this class as a non-generic class, so that we can later turn this class into a generic class, and in doing so highlight the benefits of using generics in our C# code. So let's create a public class named sortArray. Let's create a public method within the sortArray class named BubbleSort. This method does not return a value and contains a parameter which is an array defined as the system.object type. Remember, we are first implementing our code in a non-generic way. We want to be able to sort an array of any built-in value type, string type, and even user-defined types. We are using the object data type rather than generics to enable sorting arrays of varying data types. We are able to achieve this because all managed data types in C# ultimately inherit from the system.object data type. For value types, boxing functionality can be applied to store value type values inside an object reference type. For more information on boxing and unboxing, please click the card in the top right-hand corner of your screen to watch the first part of this tutorial on C# generics. A link to this video has also been included below in the description. So let's write the code for the BubbleSort method. Firstly, let's set a local variable of the integer data type to the length of the array that will be sorted by our BubbleSort code. This is the array that will be passed into this method at runtime. We are now going to create two for loops, an outer loop and an inner loop. Let's create the outer loop first. So this loop simply traverses all the elements of the array that will be passed into this method at runtime. For every traversal of the outer loop, the inner loop traverses all the elements of the array minus the current value of the outer loop's incremented value, in this case an integer value stored in a local variable named I. And of course we know that the -1 in both the outer and inner loops is there because arrays in C# are zero-based. So now, within the inner loop, we can write the code that compares the current element's value, i.e. the value currently being traversed, with the value of the adjacent element in the relevant array. So we can get the adjacent element by adding 1 to the value stored in the j variable, which is being incremented by the inner for loop statement. So notice the red squiggly line when we try to perform our comparison code using the greater than symbol. This is because the object type does not support the use of this operator for comparing one object value to another. So value types like, for example, int, float, long, etc., and the string data type implement the iComparable interface. So we should be able to use the Compareto method to perform the comparison functionality we need for our BubbleSort algorithm. The Compareto method definition is a member of the iComparable interface. The system.object type does not implement the iComparable interface, so we need to perform a runtime casting operation in order to use the Compareto method. This highlights the danger of using the object data type in code like this, because we are assuming that the elements of the array passed into this method at runtime will implement the iComparable interface. So this code runs the risk of causing a runtime error and at the very least carries the performance overhead incurred when the casting operation is performed at runtime. So we can perform the casting operation like this. The way the Compareto method works is that the current value is compared to another value. And if the current value is greater in value than the other value, an integer value greater than 0 is returned to the calling code. If the values are equal, an integer value of 0 is returned from the Compareto method to the calling code. If the current value is less than the other value that it is being compared to, the Compareto method returns an integer value less than 0 to the calling code. So with regards to the BubbleSort algorithm, if the Compareto method returns a value greater than 0, this means that the current value is greater than the value it is being compared to, and the two elements need to be swapped in terms of their positions in the array. So let's write the code for this. Let's set a variable named temp to the value of the current item being traversed. Let's then set the value for the current item in the array to the value of the adjacent item in the array, i.e. the value that the current item is being compared to. Then let's set the adjacent item's value in the array to the current item's value in the array, i.e. the value that is stored in the temp variable. So in effect, we have simply swapped the positions of two adjacent values in the relevant array. So in the interests of cleaner code, let's encapsulate this swapping functionality in a private method named swap. And that's it. We have implemented our BubbleSort algorithm. So let's go to the main method and write code to test our sort array class. Let's create an array of integer values where the values are stored in no particular order. Let's write code to instantiate an object of the sort array type. Let's write code to invoke the BubbleSort method and pass in the relevant array that we want sorted. Okay, there's a red squiggly line under the passed in array argument to the BubbleSort method in our code. This is because we need to change our definition of the relevant integer array to an object array. Let's write the code to write the value stored in the relevant array to the console screen. Let's run the code. Great, and we can see that the values have been appropriately sorted. Let's test our BubbleSort functionality for an array of strings. Let's run the code. Great. And let's now test our BubbleSort code for an array of a particular user-defined type. Let's create our user-defined type. So let's create a class named employee. This will be the user-defined type that we'll use for this example where our BubbleSort code sorts an array of a particular user-defined type. Let's keep this class simple and give it two auto-implemented properties, ID as int, name as string. Let's go to the main method and create an array of employee objects. I'm going to add made-up data for each employee object, and these employee objects are deliberately unordered. Let's run the code. And we are getting a runtime error. This is because our BubbleSort code relies on the Compareto method to compare the relevant values in the relevant array. This means that the object stored within the relevant array must implement the iComparable interface. This highlights one of the reasons why our code should implement generics. We'll implement the generic version of this code in a bit. For now, to fix the runtime error, let's make the employee class implement the iComparable interface. Let's hover our mouse pointers over the red squiggly line under iComparable, click Show Potential Fixes, then let's click Implement Interface. We can now see that Visual Studio has created a method named Compareto. So we must implement code here that compares the current object's ID with the ID of the object passed into the Compareto method. So to get the current object, we can simply use the this keyword. The object that we'll compare our current object to is the object that will be passed into the parameter named obj, which is a parameter contained within the Compareto method. As you can see, the relevant parameter named obj is of type object, so we need to typecast this object to employee. Notice that we need to perform a lot of runtime casting to make this code work. This is not a good thing, and we'll solve this problem in a bit using generics. So, we are going to sort the employee objects in the relevant array by their ID properties. The ID property is of type integer. Integers in C# implement the Compareto method, so we can simply write code to return the result of the Compareto method to the calling code like this. So this code simply compares the ID of one employee object with the ID of another employee object and returns an appropriate value to the calling code. As stated earlier, a value greater than 0 if the current employee object's ID is greater than the other employee object's ID. 0 if they are equal in value, and a value less than 0 if the current employee object's ID is less than the employee object ID that the current employee object's ID is being compared to. The string data type also implements the iComparable interface, so we could replace this code with similar code that compares the current employee object's name property with the other employee object's name property. We'll test this a bit later. I'm also going to override the toString method in the employee class so that we can display the employee object's ID property followed by the employee object's name property when an employee item's values are written to the console screen. So when we write an employee item to the console screen, both the ID and the name properties of the relevant employee objects will be outputted to the screen. So let's run the code. Okay, so this is not the result we expected. In order for our override of the toString method to be executed, we need to typecast the item we are writing to the screen to the employee type. Note the need for more bad typecasting code. Let's try again. And now our code works as expected. You can see that the employee objects within the array have been ordered by their ID properties as expected. Great! So the sortArray class now works for multiple data types. We have achieved this functionality by using the system.object type. This is because all managed data types in C# ultimately inherit from the system.object type. For more information on C# data types, please click the card made available in the top right-hand corner of your screen to view a video on C# data types. So let's see how we can achieve the same functionality but through the use of generics. We'll also see why it is more advantageous to use generics to avoid the performance penalties incurred by using the system.object type to achieve the desired functionality. So through our use of generics, we can also eliminate the risk of data type-related runtime errors. So let's change our sortArray class into a generic class. We can do this by adding a placeholder represented by a capital T within angle brackets after the sortArray class name in our class definition. Let's then replace all of our object type definitions with the placeholder data type represented by the capital T in our code. In the main method, we must add angle brackets after the sortArray type when we instantiate an object of type sortArray, like this. Within the angle brackets, we must include the relevant data type to strongly type the class. In this case, we are sorting an array of employee objects, so we must include the employee data type within angle brackets. We can now remove the casting operation from the code that writes the employee data to the console screen. Let's run the code. Great! We are using generics now, so let's remove the typecasting functionality where we are casting type object to type iComparable in the BubbleSort method. Oh, but we now have a red squiggly line under the Compareto method call within the BubbleSort method. The red squiggly line is a result of the fact that we have not told the C# compiler that type T implements the iComparable interface which contains the Compareto method. So you'll notice when we add a dot after an item referenced in our array, the Compareto method is not available in the IntelliSense drop-down list. This is because Visual Studio and the C# compiler has no way of knowing that type T implements the iComparable interface. So, how can we declare that type T implements the iComparable interface? We can do this through the implementation of a constraint. By adding a constraint, we are constraining our T-type parameter to a rule that any type passed as an argument to the T parameter must implement the iComparable interface. So to add the desired constraint, we can add the following code to our sortArray class definition, where space T colon iComparable. So we have now implemented the desired constraint for our generic sortArray class, and the red squiggly line goes away. And now, if we add a dot after our item referenced in the relevant array, we can see the Compareto method, which is a member of the iComparable interface in our IntelliSense drop-down list. So let's go to the main method. Let's first test our new generic version of the sortArray class that now contains a constraint with an array of integers. Now that we are using generics to implement the sortArray class, we can use the int type to declare our array of integers rather than the object type. So notice how we are passing in the int data type between the angle brackets for the code that instantiates the sortArray class. We are now able to strongly type our sortArray class. Let's test the code. Great! Let's test our string array, so this time we must include the string data type within angle brackets when we instantiate the sortArray class. Great! And then let's test our code with our array containing values of the user-defined type employee. But before we do this, you'll notice that we currently need to perform a conversion operation within the Compareto method of the employee class to convert the obj argument, which is defined as object, to an employee type. We don't want this extra overhead caused by the casting operation at runtime. So to solve this problem, we can implement the generic version of the iComparable interface. We can pass the employee data type as an argument to the generic version of the iComparable interface like this. So let's modify our code so that we are implementing the Compareto method contained within the generic version of the iComparable interface. To do this, let's first comment out our current Compareto method. Let's then hover our mouse pointers over the red squiggly line in our class definition. Click Show Potential Fixes and then click Implement Interface. You'll notice that the new version of the Compareto method generated by Visual Studio contains a parameter that is strongly typed with the employee user-defined type. So let's copy our old implementation of the Compareto method and paste it into our new version of the Compareto method. We can now remove the casting operation from our new strongly typed version of the Compareto method. So now there is a red squiggly line under the employee type being passed as a data type argument to the sortArray class in our main method. This is because in our sortArray class definition, we have a constraint which enforces a rule at compile time that any type passed into the sortArray class must implement the iComparable interface. Our employee class is now implementing the generic version of the iComparable interface. So we need to modify our constraint in our sortArray class definition to establish a rule that any data type passed to the relevant T data type parameter must implement the generic version of the iComparable interface. So, our constraint now pertains to any type that implements the generic iComparable interface. Following this modification, our code will still work for the integer data type, which is a value type, and the string data type, because both the int data type and the string data type implement the generic version of the iComparable interface. Our sortArray class will also work for any user-defined type, like our employee type, that appropriately implements the generic version of the iComparable interface. Let's test our code. Great! So let's say we want to sort our employee objects by name. To achieve this, we can simply change the implementation of the Compareto method within the employee class, like this. Let's test the code. Great! Let's also test the code for an integer array. Let's firstly select the int data type in our code, right-click on it, and then select Go to Definition. You can see the int data type implements the non-generic version of the iComparable interface and also implements the generic version of the iComparable interface. Let's run the code. Great! Let's also test the code for a string array. Great! So we have written a generic class that can sort an array of any built-in value type, string data type, as well as any user-defined type that appropriately implements the iComparable generic interface. By using generics, we eliminated the need for a lot of type conversion operations, which would be performed at runtime and carries the risk of incurring runtime errors. Using generics can also enhance the performance of your application because the .NET runtime no longer has the overhead of performing these casting operations at runtime. Generics allows us to defer type specifications for a unit of code. This allows us to strongly type a unit of code, for example, a class, method, or collection type, at compile time. This means generics inherently has the advantage of compile time data checks to prevent the possibility of type-related runtime errors occurring. We used a constraint to indicate to the compiler that the generic type parameter, represented by the capital T between angle brackets in our class definition, must implement the generic iComparable interface. This allowed Visual Studio to make available the Compareto method on an object defined as T through IntelliSense, and ensured that the Compareto method is available on all relevant elements within the relevant array, which are of type T, at runtime. So generics and the use of a constraint has been implemented so that we can implement one pattern of logic, in this case the BubbleSort algorithm, for any C# built-in value type, e.g. int, long, float, double, etc., the string data type, as well as any user-defined type that appropriately implements the generic iComparable interface. I hope you've enjoyed this video on using generics with constraints in C#. In the next video, we'll delve deeper into generics. For more videos on advanced C# concepts and much more, please consider subscribing. And please ring the bell so that you'll be notified of future content released from this channel. If you feel you've gained value from viewing this video, please hit the like button. It will be greatly appreciated. Please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. Your comments are of course welcome. The code created for this tutorial can be downloaded from GitHub. Please see a link to the relevant repository below in the description. Thank you and take care.